Hi everyone, my name's Aman and today I'm going to be leading this GCSE Chemistry session on reactions and energy changes. I'm sure you've been with me before when we've done lots of other chemistry sessions. As usual, it will last 1 hour until 4:15 and it is the last session of today. We are moving on to a different topic today, so we've been doing structure and bonding for the last couple of weeks, but we are moving on to reactions as the next kind of broad topic. Specifically reactions and energy changes. As usual, if you just pop any questions that you have into the chat or the Q&A, and I'll try and pick them up as we're going along. And if there are any kind of my tutor questions, Bola is around to answer any of those as well. So just pop those into either the chat or the Q&A function. So as I'm sure you're aware, I study medicine at King's College London, and I've done over 150 sessions with my tutor, and I've run all of the chemistry webinars so far. So on to today's session then. The learning objectives for today are that we're going to be defining the law of conservation of energy, because that's really important for all reactions. We're going to distinguish between exothermic and endothermic reactions, providing exemplar reactions for both. So these are also really important reactions, and we need to be able to distinguish between them for this whole topic, really. And then we're going to know and explain some everyday uses of both of those types of reactions. And then kind of the key part from today is being able to draw reaction profiles for both exothermic and endothermic reactions. And then hopefully we'll finish off with any exam questions. So these are all foundation tier topics, just to say. We'll be doing the higher tier topics tomorrow, where we'll be looking at bond energy calculations and explaining why exothermic reactions are the way they are and why endothermic reactions are the way they are. So starting off then by defining the law of conservation of energy. So the law of conservation of energy is a law of science that states that energy cannot be created or destroyed. And if you're studying physics, I'm sure you've come across it in physics as well. And it's very similar to the equations that we've done before, where we've said that the reactants are always equal to the products. So the law of conservation of mass. So it's very similar where the mass stays the same. Here it's about the energy changes. And the key part is in the second part of that statement, where we talk about that energy is only changed from one form into another. And what that means is that, for example, when a reaction takes place, it may change from the kinetic energy of the particles reacting to thermal energy or heat energy that's then given out. But the amount or the value of that energy will not change throughout that reaction. So it'll be the same before and after, because energy cannot be created or destroyed. Any questions about that at all? Someone's just asking, is this a foundation lesson? It's just a normal lesson, so it's not distinguished between foundation or higher. You need to know all of these topics for both foundation and higher. We'll be doing a range of questions on both. So moving on to the next part then. So what are exo and endothermic reactions? So does anyone have a good way for remembering the difference between exothermic or endothermic reactions? I learned a couple at school, and if you're studying Latin, for example, you might know how to kind of help you to tell the difference. If not, exo kind of sounds like exoskeleton. It also sounds a bit like exit. Yep, excellent. So someone's put exo is exit. That's a brilliant way to remember it. So exo is exit, and that means that heat will escape or leave. Really good answers. What about endo? What does that sound like? So we've got exo is exit. What about endo? Any ideas? Yep, enter or in. So endo kind of coming in. So either of those are really helpful just to help you in exam situations, because I know when we get a bit anxious in exam situations, we might forget or mix up the two. So if you've got something to remember that by, exo is where the reactions where we transfer energy to the surroundings. So that means energy leaves that reaction. And the key part is that the temperature of the surroundings will increase. And the products form will have a lower energy than the reactants. Now that might be a bit confusing to understand. So if we think about it this way, we've got some reactants, they're going to react together and they're going to form products. The energy that forms when those reactants react will be released into the atmosphere. And what that then means is that those products that are formed lose energy. So in exothermic reactions, the temperature of the atmosphere increases, so energy is leaving, as we know from exo, but the products will lose that energy, and so the products become lower in energy. So they have a lower temperature. When we're measuring the temperature of reactions, we don't measure the temperature of the products because we can't do that. We're measuring the temperature of the atmosphere. So if you put a thermometer in when you're doing a reaction, you'll get the reaction temperature when you start, or the atmosphere temperature when you start, and then the atmosphere temperature when you finish. And that's why in exothermic reactions, the temperature will increase, but the products will decrease in energy. The opposite is true for endothermic reactions. So we said endo is like in, and that's when energy comes in from the surroundings to those reactants, and we get a decrease in temperature. So what will happen is, because that energy is coming in from the surroundings, the products will have a higher energy. They've gained some energy from the atmosphere. So the heat energy is taken in from the surroundings. So there's two distinctions there. The first thing is that in exothermic reactions, the energy is released, and in endothermic reactions, the energy is taken in. The other thing is that in exothermic reactions, the products have a lower energy or a lower temperature, and in endothermic reactions, the products have an increased energy or increased temperature. Any questions on that at all before we move on? So that's kind of key for being able to do this whole topic. We need to be able to determine the differences between exo and endothermic reactions. Okay, so no questions there. The next thing is that a lot of the curricula want you to be able to come up with some reactions that are examples of exo and endothermic reactions. You don't need to memorize lots. All I would say is have one or two up your sleeves, just in case they ask for one in an exam question. The most common one they ask about for exothermic reactions is combustion. So what's combustion? Can anyone give me a definition of what combustion is? I've got an example of a reaction on the screen. What do we say combustion is? Yep, the burning of a fuel with oxygen. Excellent. Yep, someone's saying fire. Yep, really good. So that's what combustion is. We're burning a fuel. So here we're burning propane in oxygen to produce carbon dioxide and water, and that's a key reaction. All of the alkanes will burn in oxygen to produce carbon dioxide and water, and that is always an exothermic reaction. So that means the temperature of the surroundings will increase. The second type of reaction is a neutralization reaction. So we did neutralization on last week when we looked at concentrations, and we also did a bit yesterday as well. And you may remember that's when we react an acid with an alkali. Remember, an alkali is a base dissolved in water, and it will always produce a salt and water. So that's what we get when we do neutralization reactions, and most of them are exothermic. The reason I would say to remember combustion reactions is because all combustion reactions are exothermic, but some neutralization reactions aren't. So if you are going to remember a neutralization reaction, make sure you remember one that is exothermic. So the one that I've put on there at the moment, sodium hydroxide reacting with sulfuric acid to produce sodium sulfate and water, is an exothermic reaction. Then the final one that is usually exothermic is oxidation reactions. So what does oxidation mean? Can anyone give me the definition of oxidation? And again, it's okay if not, we've not actually covered this yet, so it's just to see if anyone knows. Okay, so we've got lots of different answers here. Bonding with oxygen, or the gain of electrons, loss of electrons. Okay, so lots. Yep, so the key kind of acronym that I learned at school was oil rig, where it says that oxidation is loss and reduction is gain. What's it the loss of? Does anyone know? So oxidation is loss, reduction is gain. So it's the loss of something. What's it the loss of? Yep, the loss of electrons. So we're gaining oxygen when we do oxidation. So if we have a look at this reaction here, we've got sodium plus oxygen. But what's happening is that sodium is losing electrons. And the way we can tell that sodium's losing electrons is that it forms sodium oxide. Remember, when sodium reacts, it only has one electron in its outer shell. It's in group 1, which means that it wants to lose one electron. And if it loses that one electron, it becomes Na+. So it's been oxidized. It's had oxygen added and it's lost an electron. Oxygen, on the other hand, becomes reduced because the oxygen will gain electrons. Remember, the oxygen forms a 2- ion. And that's why when we react them, we need 2 sodiums to react with 1 oxygen. because oxygen has 2 electrons that it wants, but sodium only has 1 that it can give. So it will do Na2O, and that's why it's sodium oxide written as it is. So oxidation is the loss of electrons, reduction is the gain. So they're the 3 types of reactions that are always, well, most of them are always exothermic. So I would remember combustion reactions if you're going to remember one, most neutralization, and the oxidation reactions, what I've put in brackets here is that it's usually when they're highly reactive. So does anyone know why sodium's highly reactive? So we went over this about 2 weeks ago. What's special about sodium? What group is it in that makes it highly reactive? It's an alkali metal, great, yep, what does that mean? Then if it's an alkali metal, why is it highly reactive? Yep, it wants to lose its outer electron, and the key thing is it's only got 1 outer electron. So remember when we talked about shielding, and we talked about the distance from the nucleus and the fact that there's only 1 electron in its outer shell, which means it's very easy for sodium to lose that electron, which makes it highly reactive. Whereas if there were more electrons, it's slightly harder to lose it. Well done, okay. So the next thing we need to cover then is endothermic reactions. Now there are fewer examples of endothermic reactions. The one that I would remember, if you're going to remember one, is thermal decomposition, the key word being thermal. So that means we need to provide heat for it to happen. So the reason I would always remember that it's thermal is that some decomposition reactions, for example, hydrogen peroxide, remember hydrogen peroxide is H2O2, which decomposes to form water and oxygen, like so. So I've not balanced that, but you can have a go at balancing it if you want. So thermal decomposition reactions are the ones that are endothermic, whereas hydrogen peroxide is not a thermal decomposition reaction, so it's not endothermic, it's actually exothermic. So if you're going to remember an endothermic reaction, make sure it's thermal. The next example is sodium carbonate and ethanoic acid. So ethanoic acid is an example of a carboxylic acid. Again, we've not gone over this topic yet, but you may have done it in chemistry at your school. It produces sodium ethanoate plus carbon dioxide plus water. And the third example is citric acid plus sodium hydrogen carbonate. This is sodium hydrogen carbonate, this is citric acid, and producing carbon dioxide and water and sodium citrate. So there are 3 examples of endothermic reactions. Did anyone have a go at balancing the hydrogen peroxide decomposition reaction? If not, we'll do it together. So remember, when we balance equations, we want our reactants and products to be the same. So at the moment, we've got 2 hydrogens, so they're balanced. 2 oxygens, but 3 oxygens over here, so we need to balance that somehow. Remember, when we have an odd number, we like to make it even. So by that, if I put a 2 here, we'd end up with 5 oxygens, so we've not made it even. That means we need to put the 2 here. And then what happens is we have 4 oxygens and 4 hydrogens. So to balance it then on the reactant side, we need to put a 2 here so that we have 4 hydrogens and 4 oxygens. Well done to the people that sent me in answers. You were exactly correct, well done. Okay, so a quick quiz then. What do you call a reaction that transfers energy to the surroundings? So which reaction transfers energy to the surroundings? Good, exothermic. So remember, exo, exit, it's exothermic reactions. What would you feel if you held a beaker of potassium nitrate dissolving in water? So you're holding a beaker of potassium nitrate, it dissolves in water, and we've been told it's an endothermic reaction. What would you feel? Okay, so we've got a few balanced answers here. So someone's saying colder, someone's saying hotter. So it's an endothermic reaction. So that means heat is taken in. So the products will be hotter, but the atmosphere will be colder. And remember, we feel the atmosphere, we're not going to feel the products. So actually, when you feel that beaker, it's going to feel cold. So the people that said cold, well done. So remember, there's 2 distinguishments between exothermic and endothermic. In exothermic, the atmosphere gets hotter. In endothermic, the atmosphere gets colder. And that's what we measure with a thermometer, and that's also what we feel. But the actual products will have an increase in energy in endothermic reactions, but a decrease in energy in exothermic reactions. Good, well done. Okay, The final question then, two solutions are added together and the temperature changes from 14 degrees to 28 degrees. What can we deduce about this reaction? So what do we know about that reaction then? So two solutions, they're added together. The temperature has gone from 14 degrees to 28 degrees. Exothermic, excellent. So the temperature has increased. And remember, when the temperature increases, it's exothermic. Brilliant, well done. Someone is asking me, am I breaking up? Can everyone hear me okay, or am I breaking up? And another person is asking, is the last equation not an endothermic reaction? Okay, so people can hear me, that's fine. So this equation that we did on hydrogen peroxide is exothermic. I was giving the difference between thermal decomposition and decomposition. Thermal decomposition reactions are endothermic, and it must be thermal, whereas hydrogen peroxide decomposing are not thermal decomposition reactions, and therefore they're just plain decomposition reactions, so they are exothermic. So that was the example I was giving there. Okay, great. So I'm now going to show you a video, but before I show you that video, I've already talked about using a thermometer to measure the temperature of our reactants and our products and what happens with regards to atmosphere changes. How do we do that reaction? Can anyone give me a step-by-step guide of how we do that reaction? So for example, if we go to, let's say we're burning propane and oxygen together, and we want to know the temperature changes, what equipment do we need and how would we know that it's exothermic? So we're reacting propane and oxygen. What equipment would we need? You can do either or, you can do the neutralization reaction or that. We definitely need a thermometer, yep, and what's that thermometer going to show throughout that reaction? For an exothermic reaction, what's it going to show? We've got a thermometer in a beaker. For example, we've got two reactants reacting together. It's an exothermic reaction. What's the thermometer going to show as the reaction? Good, we do the start and the end temperature and then you work out the difference. Excellent, well done. So you want the start and end temperature. So the reason I'm asking that is because a lot of exam questions on this topic will ask you specifically how to carry out the experiments. And it's important you always say you're using a thermometer, you need the start temperature and the end temperature, and then you work out the difference. And if the temperature increases, it's exothermic. If it decreases, it's endothermic. Well done, people that give me answers, you're exactly correct, well done. Good, so let's watch a quick video then on one of these reactions. Okay. So we can see that at the moment we've got a couple of beakers. So we've got vinegar. Being put in a beaker. And then we're going to add some of the, well, actually she's first going to take the temperature. So that's our start temperature that's being recorded now. And that's important. Before they add the second reactant, they've taken the start temperature, and that's because if they add the second reactant, the reaction will start. So we need the reaction temperature before we add that second reactant. So now we're just measuring out the second reactant. It's baking soda, so I'm sure some of you might have done this at school. So baking soda and vinegar tends to be quite a violent reaction. Okay, so we're adding it now. You see that nice effervescence. Remember, that means bubbling. So what happened to that temperature? Did anyone remember the first temperature? What's happened to that temperature there? So it started off at about what, and what's happened to it? Well, we can see it's going down. Good. I'm going to stop the video there. Good, it's an endothermic reaction. Well done, everyone. So the temperature decreased. So vinegar reacting with baking soda is an endothermic reaction and the temperature has decreased. So that's how you would do it at school. So you measure the temperature using a thermometer first. You then add the second reactant in and then you measure as the reaction finishes. And it's really important you get the end temperature. So I didn't let the video go to the end temperature, but you wait until all the reactants have finished reacting and all the products are formed. Excellent. So some uses for exothermic reactions then. So there are always exam questions on uses. The first one you probably might have used are hand warmers. So hand warmers are usually based on sodium ethanoate. Sodium ethanoate, we went through the reaction of it as an exothermic reaction. So the reason we use them in hand warmers is because A, they're not dangerous, and B, they heat up very quickly and they can last for about 30 minutes. So what we do is, if you can see this metal disc over here on the screen, that metal disc tends to have some of that metal on it, so some of the sodium. And this pink over here will be the dissolved solution. So remember, it's sodium reacting with ethanoic acid to produce sodium ethanoate. So there'll be ethanoic acid there dissolved in water. And when you then click this metal disc, some of those metal particles will come off that disc and react with the ethanoic acid in there, producing the salt sodium ethanoate, and that produces crystals. So if you've ever had one of these hand warmers, you know it goes from being kind of this squidgy material going to a really hard material, and that's because loads of crystals form. And that's strongly exothermic, so it will stay hot for about 30 minutes. And if you've also had one of these, you'll know that to get it back to its normal form, because it is reusable, we just put it in a pan of boiling water, and all that does is it heats up the sodium ethanoate and basically separates the sodium from the ethanoic acid again, so that it goes back to being as it was at the beginning. And then if you click the metal disc again, some sodium will come off and again react with the ethanoic acid. So that's one of the main uses of exothermic reactions that's non-dangerous. The second one that you may or may not have heard of is self-heating cans. We don't have many of those in the UK, but they have been used across the world. So self-heating cans basically heat up food, and they do what they say. They heat themselves up without having to use a microwave or an oven. They are usually based on calcium oxide and water. And usually how they work is that there'll be a button somewhere on the can. And when you click that button, it allows the calcium oxide and water to react. And when they react, it produces calcium hydroxide. And I've put there coffee. So one of the main uses in the UK is for self-heating coffee, but we don't tend to have many food items that are used in the UK for self-heating. So hopefully what you can see as kind of the common things between these two is that it's always you're producing some kind of reaction, either by clicking a button or clicking that metal disc in the hand warmer. Any questions about those uses of exothermic reactions at all? No? Okay. So the next thing then we'll go on to is endothermic reactions and some of the uses of those. So the two things that we need to know about are cold packs. So often in sports injuries, or for example, if you've got swollen limbs, you'll use an ice pack. But if we haven't got ice pack to hand, because for example, we haven't got a freezer at sports events, for example, then we use these chemical cold packs. And what they do, they tend to have ammonium nitrate and water in them, and they'll be completely separated. So the ammonium nitrate and water will be separated. But if we hit that cold pack or kind of move it around a lot, what will happen is that the ammonium nitrate and the water will be allowed to react. And because it's an endothermic reaction, the temperature will decrease. Someone's saying they are like opposites. Yeah, exactly, they are like opposites. And then the next thing is chilled drink cans. So these are like those self-heating cans. It's the same with chilled drink cans. It's an endothermic reaction going on. And usually they're based on some kind of endothermic reaction. It can be ammonium nitrate and water because that's a safe one. But usually it's in there. Again, you click a button, it allows the ammonium nitrate and water to come into contact and react together. Okay, so that's the uses of both exothermic and endothermic. And as I said, it's always about the reaction taking place, and usually something has to happen to kind of start off that reaction. It's not just going to happen on its own. So then the next thing we're going to cover is the reaction profiles for exothermic and endothermic reactions. But before we go into that, are there any questions on what we've covered so far? So first of all, we've already defined what exothermic and endothermic reactions are. We know what the law of conservation of energy is. And therefore that states that energy cannot be lost, it always stays the same, it can just be transferred into different forms. And we've covered some of the common uses of exothermic and endothermic reactions, and also some of the common examples of those reactions. So then reaction profiles. So you may have seen a diagram that looks like this. And this is what we call a reaction profile. As I said, it's in all of the common examples, so AQA, OCR, and Edexcel. And you need to be able to label this diagram. So I thought that there are 4 things that you need to be able to label. The first one is this. The second one is this. The third one is something called the activation energy. And the fourth one is something called the overall energy. So let's start with the first arrow over here. Does anyone have any idea what the first arrow is? What am I trying to label there? Okay, someone's asking a very good question. They said, I'm just a bit confused. For endothermic reactions, if they take in energy from the surroundings, wouldn't that mean that they get warmer? That's a really good question. So what's actually happening is that because they're taking in energy from the surroundings, that doesn't necessarily mean that the products are getting warmer. Remember then that the energy changes doesn't have to be thermal energy. So the products could be taking in kinetic energy. But what is definitely happening is that the atmosphere is losing energy, and it's losing thermal energy specifically. So they take in thermal energy, but remember that energy can be transferred. So yes, the products will increase in temperature slightly, but they won't increase enough like an exothermic reaction. So hopefully that makes sense. So remember, the products are taking in energy. It's not always thermal energy, which means that the products do not increase in temperature, but the atmosphere decreases in temperature. So in endothermic reactions, the overall energy change is a reduction in thermal energy. If you look at the exothermic reaction that's going on here, this is potential energy. So hopefully it will now make sense why products are not hotter. So let's think about exothermic first. So someone said reactants is the first arrow, which is great. So the reactants is what goes on the first part of that diagram. Okay, if we know the first arrow is reactants, what do you think the second arrow is? Products, brilliant. Okay, so let's first of all think, why are the reactants higher than the products? So we know in exothermic reactions, the atmosphere increases in temperature. But remember I said that the products decrease in temperature, or they decrease in energy. And that's because they lose that energy to the atmosphere. So someone's asking, are all decompositions exothermic reactions? That's a very good question. All thermal decompositions are endothermic. Most of the other decompositions that aren't thermal decomposition reactions are exothermic. Yes, excellent. So the reaction loses energy, specifically the products lose energy. So any energy that the products had is being lost into the atmosphere. So actually the products lose energy, but the atmosphere increases in temperature. And that's why when we measure the reaction temperature change, it will always increase. But on this reaction profile, we're thinking about potential energy. Remember, that relates to the particles. So the products will have a reduction in energy because they've lost it to the atmosphere. Okay, the third thing then to be able to label on this diagram is the activation energy. Before we label the activation energy, does anyone know the definition of activation energy? How do we define the activation energy? It's a key term that we use when we're thinking about reaction profiles. Okay, someone said the energy needed to start a reaction. Good, the energy required to turn reactants into products. Okay, we need a little bit more. Brilliant. So someone said the minimum amount of energy required to start a reaction. Excellent. So that's the perfect definition. So I'll type that out. It's the minimum energy. So the minimum amount of energy required to start a reaction. So it's not just the energy, it's the minimum amount. So remember, in reactions, sometimes we do need to provide heat. On reaction profiles, they will always show that we do need to provide some energy, usually in the form of heat. And when we heat up our reactants, they will then react. And that heat that we supply is called the activation energy. But obviously we can supply more, and therefore the activation energy is the minimum amount of energy that needs to be supplied to allow those reactants to react. So that's what the activation energy is. Does anyone know where on the reaction profile the activation energy is? And I appreciate it's quite hard to describe, so do your best. Does anyone know where it would be? brilliant. So some people are saying just underneath the peak, from the reactant energy level to the peak of the curve. Yep, excellent description. So the activation energy is from the peak all the way down to the reactants. So let me just draw that as a straighter line. There we go. So the peak of the curve here, all the way down to the reactants. So remember, the reactants will start off at a specific energy level. We then add energy in, and the amount of energy we need to add is at the peak of that curve. When we add that amount of energy, suddenly those reactants are going to react. And then all of a sudden, because the reactants are reacting, they're losing energy to the atmosphere, and then the energy is being lost. So the products have a lower energy. So that's how we describe an exothermic reaction profile. Okay, the final thing we need to be able to label then is the overall energy change. Does anyone know where the overall energy change is on the diagram? Where do we label that? The overall energy change. Or can anyone describe it to me? So the overall energy change, we've labeled the reactants, we've labeled the products, and we've labeled the activation energy. Excellent. So someone said from the reactants line to the products line. Yep, brilliant. And the key thing is it will always have a direction. So in exothermic reactions, it's downwards. And that's because the energy decreases. So this is the overall energy. And the dark blue line is the activation energy. So this here is the activation energy. So they are the four things that you need to be able to label and also recognize on a reaction profile. Some questions will ask you to draw the whole profile. Again, it's not about being neat. Just make sure you've got two straight lines for the reactants and products, and you've got a nice curved line between them. Remember, the products are always going to be lower than the reactants in exothermic reactions. Excellent. So now let's do the other graph then, which are endothermic reactions. So again, there are 4 points to label. First, we've got to label the reactants and products, then the activation energy, and then the overall energy change. So let's start off then with the reactants. Where are the reactants? Someone's saying EA, is that a shortened form of activation energy? Yes, it is. So the big E always usually stands for energy, the small a is activation. So where are the reactants going to be on this diagram? What do we think? Someone's saying the opposite formation of exothermic reactions. So does that mean then that the reactants are here? Is that what we think, that the reactants are there? Okay, brilliant. Yep, it's the first flat line. So it's not quite the opposite. The reactants and products pretty much stay where they should be. So reactants are here and products are here. So just like in the exothermic, so if I go back to exothermic, reactants are the first line, products are the second line. So it's the same with endothermic. So here's our reactants, here's our products. Okay, the next thing we need to label then is the activation energy. Someone's asking, why is there more product than reactant? That's a really good question. What do you mean by that? Do you just mean that this line is slightly longer? Or are you talking about why is the product higher than the reactant? Okay, so why is the product higher than the reactant? The product is higher than the reactant because in endothermic reactions, remember what happens is that we take energy in from the atmosphere. So the temperature of the atmosphere decreases, but the products increase in energy because they're taking that energy in. Remember, that doesn't necessarily mean that they increase in temperature because it's potential energy. Remember, energy can be transferred from one form to another. So they take in thermal energy from the atmosphere, but it's produced as potential energy in the products. So the products don't increase in energy, all right? Okay, then we've got the activation energy. So someone's saying it's near the reactants line. Yeah, so it's exactly the same as on the exothermic reaction. It's always from the reactants to the peak of the curve. Just like that. So that's the activation energy. And we can label it EA. So that's just a shortened form of activation energy. So the big E always means energy and the A stands for activation. Okay, so the final thing then is, what is the overall energy change in this reaction? Where do we label that? Any ideas? Where do we label the overall energy change? So we've got the activation energy, we've got the reactants and the products. The final thing we need to know is the overall energy change in endothermic reactions. And remember, this is the overall energy change with relation to the reactants and the products, not the atmosphere. So everything we've been talking about so far with regards to how we measure it at school is to do with the atmosphere and thermometer changes. So on a thermometer, like the YouTube video I showed you, it showed that the temperature decreased. But on a reaction profile, we can see that the products are higher than the reactants. Great, so someone is saying gap between the reactants and the products, upward arrow. Someone's asking how much reactant compared to how much product will show the energy change. Good, well done. So sorry, I thought that was a question, but it's not. Yeah, so it's an arrow like that, and it's always upwards because we are gaining energy in endothermic reactions. Will the numbers of the arrows on the lines affect anything? Will the numbers, what do you mean by the numbers of the arrows on the lines? Okay, excellent. So we've got our activation energy, we've got our overall energy change, and we've now done that for exo and endothermic reactions. So just as a quick recap, our exothermic reaction, the reactants start off at a higher energy. We then add in our energy to get the reaction to start. That's called the activation energy. It's the minimum amount of energy required to start that reaction. Once we've got to that peak, we've started the reaction, all of a sudden the energy is going to go down, and that's because energy is being lost to the atmosphere. So the atmosphere will increase in temperature, but the products will lose energy, and it's in the form of potential energy. So the overall energy change is a decrease, as shown by this arrow, this pink arrow, it's decreased. Excellent. Brilliant. And then for endothermic reactions, here we can see the reactants start off lower than the products. Usually they require a bit more activation energy to get them to react, so we need more energy in there. Once they start reacting, they will lose energy, but nowhere near as much as exothermic reactions. And in fact, as a general rule, they've gained more energy than they had at the start. And so the products have more potential energy, but they've gained that energy from the atmosphere, so the atmosphere decreases in temperature. Okay, well done everyone for being able to fill that in. That was really good. So now we'll go on to do some exam questions. And before we do that, does anyone have any questions on any of the content that we've covered today? Otherwise, we'll go in and do some exam questions. No? Okay. So this is our first question. It's about the reaction of ethene and bromine. Someone's asking, what level is this? So as I said, this is not higher or foundation tier, it's kind of in between. This would be about a grade 5 or 6 topic. So this question is about the reaction of ethene and bromine. The equation for the reaction is here. So we've got ethene reacting with bromine. Complete the reaction profile in figure 1. So what we can see is that we've got our reactants and our products. From looking at that, what type of reaction is it? Our reactants are higher than our products. What type of reaction is it? What do we think? What type of reaction is that? Exothermic, excellent, well done. Someone said endothermic, not quite. So remember, it's exothermic because the products will lose energy, but the atmosphere will increase in temperature. So right at the beginning, I went through, there's 2 distinct differences between exo and endothermic. In exothermic, the products will have less energy, but the atmosphere will increase in temperature. In endothermic, the products will have more energy, but the atmosphere will be colder. Yeah, so someone's asking, are we doing about bonds tomorrow, because they don't understand that bit. Yeah, no, don't worry, and don't apologize for asking questions, that's absolutely fine. Yeah, we'll be doing, explaining about why reactions are exo and endothermic tomorrow, and specifically about bond energy calculations as well. So yeah, this is an exothermic reaction, and the reason we know that is that the reactants start off at a higher energy than the products. So energy is being lost into the atmosphere, so it's an exothermic reaction. We need to draw labeled arrows to show the energy given out and the activation energy. So let's start with the activation energy. where would the activation energy be? So there's something missing on the diagram that we also need to draw. So first it's saying complete the reaction profile. So how do we complete that? What's the first thing we have to do before we can draw the labeled arrows? What do you think? We've got our two reactants. Draw the peak. Excellent. Well done. So to draw the peak, remember, it doesn't need to be done very neatly. It just needs to be a line that looks something like that. So it's going to go up and come down from the reactants to the products. Brilliant. Okay. So where's the activation energy? Where's that going to be on this diagram? And where's the overall energy given out? So they've been nice, they've told you it's energy given out. Good, from reactants to peak is the activation energy. So on this exam question, from here to here would be your activation energy, which I've just abbreviated to EA. And then what about the energy given out? What do we think? Where would that be? So the energy given out is another term for the overall energy change. So effectively in this graph, it would be from the reactants to the products down like that, and it's overall energy. You need to make sure it's a downwards arrow to show that energy is being lost and therefore given out. Excellent. So let's go on to the next question. So how does the energy level diagram on the screen show that the reaction is exothermic? How do you think we can answer that question? What do we need to say? How does that energy level diagram show that the reaction is exothermic? Yeah, so someone said the reactants are higher than the products, almost there. So what we need to be able to say is that the reactants have a higher potential energy than the products, and it's important to talk about it in terms of energy. Someone said exothermic decreases in temperature while endothermic increases. Not quite. So it's not about temperature changes on this reaction profile. It's about potential energy changes. So exothermic reactions increase in temperature because the atmosphere gains thermal energy, but the products lose energy because it's all given out to the atmosphere. So they lose it, and that's why the potential energy decreases. Whereas endothermic reactions will decrease temperature from the atmosphere, but the actual products will have a higher potential energy. So I'm just going to type that out because I think quite a few students are getting confused. So remember, there's two differences. So exothermic reactions will increase the temperature of the atmosphere, and therefore the products lose potential energy. So what that means is because they lose potential energy, they have a lower energy than the reactants, because don't forget, the atmosphere is increasing in temperature. That means all the energy that the products had is being lost to the atmosphere. Whereas endothermic reactions will decrease the temperature of the atmosphere because they take the thermal energy in and convert it to potential energy. So the products don't have thermal energy, they have potential energy. So they take the temperature of the atmosphere decreases because they're taking in that energy from the atmosphere, and it's being converted to potential energy in the products. Brilliant, well done. Okay, so this is an exothermic reaction, and as I said, the way to describe this reaction or to say that it's exothermic is that the reactants have a higher energy or potential energy than the products. So before we continue with this question, does anyone have any Q&A questions? Because it is Q&A time, so if anyone's got any, if you pop them into the Q&A or the chat function, I'll answer them now. So that's about anything from today or previous sessions that you have. As long as it's chemistry related, I'll answer it. So as I said, just pop them into the Q&A or the chat function if you've got any questions from today. Okay, so it doesn't seem that there are any questions. If you do have any, just pop them in and we'll continue with our exam questions. Okay, so we've got magnesium burning in air. How can we tell that a chemical reaction is taking place? So from that picture, how can we tell? Okay, someone's asking, can you show us the energy diagram for an exothermic reaction and endothermic? Yep, I can go back to those slides. So this is the exothermic energy diagram. So we start with our reactants. We heat up those reactants. That's where our activation energy is. So this dark blue line is the activation energy. It's the minimum amount of energy required to start a reaction. When that reaction starts, straight away when the reactants react together, energy will be lost to the atmosphere. And that's why the atmosphere increases in temperature. But as energy is lost to the atmosphere, the products will obviously lose that energy because it's being lost to the atmosphere. So in the overall reaction, the products will have a lower potential energy. And so the overall energy change is a decrease. That's exothermic. And then endothermic reactions, the reactants start off, we put in our activation energy. And again, when we start the reaction, it does lose energy. That's just because we put in a lot of activation energy. And obviously, if we stop putting in activation energy, or we stop heating up, for example, it will lose heat. And as they react, they will lose some energy, but they won't lose that much because most of all, they're actually accepting energy from the atmosphere. So the atmosphere decreases in temperature, and the products will gain that energy from the atmosphere. Someone's asking, what will be the hardest type of question on this topic? So this specific topic that we're doing now won't get much harder than being able to label a diagram and specifically the activation energy, the overall energy change, and then being able to calculate the overall energy change, which is just like we did on the quiz question, the temperature difference from the reactants to the products. Tomorrow, we'll be going into the higher tier questions where we talk about bond energy calculations, which are quite tricky. So someone has answered the exam question. That's great, your answer is correct. So the bright spark shows the reaction. I'll go back to that question in just a second. Someone's asking, will we do electrolysis in the future? Sorry, it has nothing to do with today's topic. That's absolutely fine. Yeah, we'll try and do electrolysis in the future. It's not coming up this week or next week, but hopefully in the future we will cover it. And someone's asking, what does EA mean? It's just a shortened form of activation energy. Really great questions. So thank you. Okay, so yeah, let's go back to this question. How can we tell that a chemical reaction is taking place? How can we tell from that a chemical reaction is taking place? So someone has said that the bright spark shows the reaction. Okay, great. So we can say there's a bright spark. What else is going on? What's this over here? The smoke. Yeah, so what does the smoke usually mean? If something is smoking, a gas has been released, it's burning, good. So what does that tell us about the temperature? Increase, yeah, it's hot. And we would expect that, there's a Bunsen burner there. So something is burning, and we've got a gas being released. So any of those answers would be absolutely fine. So you can talk about the spark, you can talk about it burning, you can talk about a gas being released. I like the spark answer because you can see the white light there. Great, and this is magnesium burning in oxygen. So if you think back to when we did our periodic table lessons, does anyone remember what the product would be? So magnesium reacting with oxygen. Brilliant, so someone said magnesium oxide. Yep, excellent, that's exactly correct. Remember, alkali metals as well as group 2 metals will usually react with oxygen to produce an oxide. And in this case, it's magnesium oxide. Brilliant, okay. The magnesium needed heating before it could react. What does that tell us about the reaction? So it needed heating before it could react. Does that tell us that the reaction is reversible? Does it tell us that the reaction has a high activation energy? Does it tell us that the reaction is exothermic, or does it tell us that magnesium has a high melting point? What do we think? Okay, so we've got some differing answers. Some people are saying it has a high activation energy. Some people are saying it has a high melting point. Okay, I'll just wait for a few more answers to see what other people think. So which one do we think the energy tells us? Someone's asking, what is the question again? It says, what conclusion can we draw from the fact that magnesium needed heating before it could react? So which of these four can we tell from the fact that we needed to add energy to get magnesium to react? Okay, so most people are saying high activation energy. Brilliant. Someone's saying it's not a melting point because magnesium, sorry, it's not melting point because magnesium is not melting. Good answer, but not quite. So yes, it's high activation energy. And the reason it's not high melting point is because most metals need energy to melt. But the fact that we've added energy doesn't tell us that it has a high melting point. What it does tell us, though, is that we need activation energy to start that reaction off. A high melting point you would only be able to tell from the figures or the amount of energy you put in. The fact that we need to put energy in tells us that there's an activation energy there and it's most likely high. It's not a reversible reaction. Again, you can't tell that about the energy that you put in. And we don't know if it's exothermic because remember, on our reaction profiles, both exo and endothermic reactions have energy that we need to put in. They both have activation energies. So this is actually a question from something we did on Friday. It's about universal indicator. So if universal indicator turns blue, what's the pH value of the solution? Does anyone remember? So we went through indicators on Friday, I think. It might have been Monday. Alkali, excellent. So blue usually indicates alkali. So which pH value is alkali then? 9. Yep, excellent. So 7 is neutral, 1 and 4 are acidic, but 9 is alkali. Really good. Okay. All right, so this is another type of question that you might get. A student investigates the energy release when zinc powder reacts with copper sulfate. We can see the method there. Calculate the energy change or the change in temperature. So just go through what he did because this is what you might do in a classroom. So we've got 100 cubic centimeters of copper sulfate in a beaker. Remember, we then would measure the temperature, which is what he's done. Before he adds that reactant, he's then added the zinc powder. He stirred it, again, really important to stir to make sure that all that reactant, all the reactants react together. And he measures the highest temperature or the end temperature. So starting temperature and highest temperature are there. So what's the difference then? What is our energy change? Good, people are saying 11 degrees. Yep, so we do the end temperature or the highest temperature minus the starting temperature. So 32 minus 21, which equals 11 degrees, degrees C. So well done, good. So calculate the energy released in this reaction. So again, this kind of goes into physics now, and this type of reaction has actually been removed from the syllabus. So we're not going to do this question, but I wanted to show you it because it's been removed. So if you see exam questions on it, you won't need to do it. If, however, though, that you do see it, you would still be able to do it because they give you exactly what you need. So it says the volume of solution in centimeters cubed. And if we have a look, we had 100 centimeters cubed of copper sulfate times 4.2 times the temperature change. So you don't need any prior knowledge to be able to do it. They've given you the exact equation and they've given you what units each of them has. So if you do get given that question, because it's not on the syllabus anymore, they would tell you exactly what you need to be able to do that. Good. Okay, so before we go on to the next question, what type of reaction is it then? The starting temperature was 21. The end temperature was 32. Remember, now we're thinking about the atmosphere. We're not thinking about reaction profiles. What type of reaction is it? Exothermic. Excellent. Well done. So it's exothermic because the atmosphere has increased in temperature. So that means the products have lost energy to the atmosphere. Excellent. Well done. Okay. So this is the type of question they might ask you about a reaction now. So this is an Edexcel question. So when sodium hydroxide solution is neutralized with an acid, there is a temperature change. A student is given dilute hydrochloric acid and dilute ethanoic acid of the same concentration. Devise a plan to compare the temperature changes. So what do we think? How could we see that reaction and how could we know what the different temperature changes are? So again, this is asking about the experiment that you would carry out at school. What do we need to be able to do? And we'll make this our last question today and then we'll finish up. So if anyone has any more questions for me, just pop them into the Q&A or the chat function. So we're thinking about experimentally, how do we react to these? Brilliant. So 2 of the marks come from saying that you need a thermometer and you need a start and end temperature. So this is a 4-mark question. That gets you 2 of the marks. What else do we need to do? We've got 2 marks. We've talked about the temperature, and we've talked about the fact that we need to measure the start and end temperature. So I will type out an exemplar answer for this because I think it's important. So here we're reacting sodium hydroxide with an acid. So first of all, we want the same volume of sodium hydroxide in 2 beakers. We measure the temperature of the hydroxide in the 2 beakers. We then add each acid to one of the beakers. So we'll add, say for example, we add HCl to one beaker and ethanoic acid to the other beaker, and measure the temperature at the end of the reaction, of both reactions. And then we calculate the energy change by doing the end temperature minus the start temperature. All right, so that would get you all of those marks there, and that's kind of the main steps in one of these experiments. All right, so I think we'll stop there for today. Well done, everyone. Does anyone have any questions just before we finish? No? Okay, excellent. Well done, everyone. You did a really good job today. As I said, tomorrow we'll be looking at bond energies.
Thanks for that session, Aman. Thank you everyone for joining us. If you enjoyed this session and you're looking for more personalized learning, we do offer one-on-one tuition, which you can find out a bit more about on our site. Please do remember that all sessions are recorded, so you can rewatch them on our YouTube channel where they're uploaded. Have a lovely afternoon, everyone. Thank you all for your time. Goodbye.
Bye.
Bye.